The broadcast is now starting. All attendees are in listen-only mode.
Sorry. Good afternoon, everyone. Welcome to our presentation, to our webinar, where we are going to talk about CFturbo primarily, and then how CFturbo interacts with Ansys. So my name is Metin. I'm the principal at Ozone Engineering, and I'd like to give a brief overview of who is Ozone Engineering and what do we do. We are engineers all day. We do FEA and CFD and electromagnetics. So that's we are in simulation business, finite elements, computational fluid dynamics, and simulation of electromagnetic tools. So we are an elite channel partner for Ansys. We basically primarily sell Ansys tools, and as of a couple of months ago, we also added CFturbo tools to our portfolio. And so among the software tools, Ansys, as you may recall, Ansys has structures, fluids, electronics, high frequency, low frequency, optics, materials database, and what we call twin builder tools. Those are primary tools. On the West Coast, we cover Oregon, Nevada, and California. And on the East Coast, we operate under a different name, Mallet Technology, and we have offices in Maryland as well as North Carolina. And in Michigan, we work under the name CATFAN. And Ansys, as you may know, Ansys headquarters is in Pittsburgh, Pennsylvania, and CFturbo headquarters in the U.S. is in New York City. As a company in as Ozone Engineering, we represent both Ansys and CFturbo in these territories. And as a company, we get into a lot of semiconductor simulations. Being in Silicon Valley, that's kind of where we started. And we do a lot of solar industry simulations. We can do mono and multi-objective design optimization with any physics. And we have teams. We have mechanical engineering team. We have electrical engineering team that deals with in high frequency, low frequency electromagnetics, and we couple Ansys in biomedical industry with musculoskeletal models, and in consumer products, we get into, of course, autonomous vehicles, where there's a lot of studies right now, projects with respect to anything from crash simulation to antennas with autonomous cars. So our engineers are involved in that, and our electrical engineering group is involved in high and low frequency electromagnetics, anything that deals with human body and as well as outside the human body with respect to antennas. So antennas is a big part of our business because IoT as well as autonomous vehicles, they all require antennas. But the main topic of the day is turbomachinery. As a company, we get involved in big and small projects that involve turbomachinery. That's why we have a big interest in CFturbo and how it aligns, how it talks to Ansys software products. So CFturbo is an outstanding solution for turbomachinery design, simulation and optimization, anything from pumps, blowers, fans, compressors, and turbines. That's where CFturbo and it's used in the design. Then whatever the design that we work on, we can bring it into Ansys tools to do CFD, and maybe followed out by fluid structure interaction to do the structural simulations. So we are very excited about the engagement with CFturbo. And today in our agenda, we have 3 speakers from CFturbo. Chelsea Hall, joining us from New York City. She's going to introduce us to CFturbo. And we have Ralph Peter Mueller. He's going to talk about CFturbo tools. And we have Sasha, who's joining us all the way from Germany. He's going to talk about CFturbo and how it is integrated into Ansys. So those are all topics of interest to us. Just to give you a brief background about Chelsea Hall, who's our first speaker. She's a digital marketing strategist at CFturbo. And Chelsea joined CFturbo in 2019 as a digital marketing strategist. Her careers span both creative work and administration for arts and culture, nonprofits, political campaigns, and now the mechanical engineering industry. We're excited to have her here. And our second speaker is going to be Ralph Peter Mueller, and he is the president of CFturbo. He studied at Dresden University, fluid mechanics, thermodynamics, turbomachinery, and he has a master's degree in engineering. And he worked at General Motors for 3 years. In 1993, he founded CFD Network, which is a CFD consulting company. In 2008, Ralph became co-founder and managing director of CFturbo in Dresden, Germany. Then in 2017, he is now the president of CFturbo in New York. So he's also joining us from New York. And last but not least, the speakers is Sasha. He's a CAE engineer. He studied mechanical engineering at Dresden University of Technology with specialization in automotive engineering and the scientific focus on the simulation of internal combustion engines. He is a CAE engineer at CFturbo headquarters in Dresden, Germany since 2008. So with that, I'm going to turn it over to Chelsea. And I'm going to make presenter over here, and so that she can give us an introduction to CFturbo. So please
Thank
go
you,
ahead,
Metin.
Chelsea. Yep.
All right, welcome everyone. We again are CFturbo. And CFturbo has been on the market since 2008. We have 2 offices. As was mentioned, we're headquartered in Dresden, Germany, and also here in Brooklyn, New York. We have 3 business fields. First, we have Turbomachinery design software, which features automated workflows and custom development. Next, we offer engineering services such as CFD or FEA simulation, digital design space exploration, as well as optimization. And finally, we offer product development, which includes rapid prototype development and mechanical design and testing. So besides our own offices, we have a network of distributors around the globe. As you can see, we are the yellow dot there on the East Coast in the US, and we're really happy to be partnering now with Ozen in Silicon Valley. So we also serve various different industries, as you can see, from energy, the oil and gas sector, to chemical and process, aerospace and defense, automotive, etc. We serve customers from large corporations, small and medium businesses, as well as startups. And our software solution is made for experts and beginners. So we want people at different levels in turbomachinery design to be able to use our software. And next we have over 200 clients from all over the world that rely on our software and services. You can see customers such as Tesla, Joby, Sundyne, Samsung, LG. We are really proud to serve all of these companies. Thank you. I'll turn it over to you, Ralph.
Right. Thank you. Thank you, Metin, first, and thank you, Chelsea, for the introduction. So I will continue now with CFturbo itself, with the technical part. And first, I have some words to the CFturbo design methodology. And the input is pretty simple. You have to put in your duty point or design point. In most cases, is this the best efficiency point of the machine, which is characterized by volume flow rate or mass flow rate, head or total pressure difference, a rotational speed, and the inlet boundary conditions. And then with these 5, 6, 7 numbers, you start CFturbo, and behind of our software, there are two basic things. One, on the one hand, there are fundamental physical equations like the Bernoulli or the Euler equation, or all the conservation equations for mass, momentum, and energy. And on the other hand, we have numerous empirical correlations in it, which gives CFturbo the ability to come up with very reasonable initial designs. So this is a sort of intelligence which helps us to get 3D models, and this is what you what is the outcome. You start with a number of values, and then you end up with a 3D geometry, which can be exported later then for CAD, rapid prototyping for CFD or FEA simulations. And we will show this later in the process during a live demo in a couple of minutes. So here you see some examples which were created in CFturbo, blowers and fans of different kinds, spiral cage, automotive cooling fans, axial fans, contra-rotating fans, and normal radial industrial fans as well. So this is a large part of our business. Then here the famous compressor and turbine industry. You see on the left side 2 compressor examples made in CFturbo, and on the right side an axial turbine and a radial inflow turbine. And last but not least, we do a lot in pumps, and we are able to create nearly any kind of pumps, from axial over radial and suction pumps, multi-stage bowl diffuser pumps, but also special types like wastewater pumps or inducers. So today we talk about the workflow with Ansys, which is for us an outstanding solution, because Ansys has for many decades the turbomachinery tools, like TurboGrid or Ansys CFX, and we have written smooth interfaces to these software. And the thing is not only that we have interfaces, we can also integrate CFturbos in the Ansys world. And there are 2 options, and one option is that we work in a optimization workflow, right? So we combine a parametric design tool, which is CFturbo in this case, with the simulation tools from Ansys, like Ansys CFX or Ansys Mechanical. And this is, let's say, driven or controlled by an optimization tool called Ansys OptiSlang. And so we can make really automated optimization. And this is a very robust and intriguing way to automate turbomachinery. So, and the other way is that we work in Ansys Workbench. So there is a truly a bidirectional integration of CFturbo in Ansys Workbench. So that means that you can go back and forth and all the parameters are maintained, all the changes are maintained, and this is especially helpful for manual, but also for automated design exploration, what you could do, for example, with the Ansys Design Explorer. And this part will show my colleague Sasha later. So I would switch now to the online demo of CFturbo. And we design, as announced in our speech before, we wanted to create an axial fan today, just as an example. So you see here, this is the GUI of CFturbo, and we choose among all the others, we choose the fan model, and as shown before, right, we have to define the design point, CFturbo, and in this case here we give the volume flow rate, 3,000 cubic meters per hour, a pressure difference, 500 pascals, and the rotational speed, which is 3,500 in this case. So there's a database available for CFturbo. It's not only for air and water, it's really a large database for any kinds of fluids. But we here stay with an airflow, and then the inlet boundary conditions are written below. And what you see on the right side is immediately a sort of, you get an idea what machine type you could choose. And this is in between a mixed flow and an axial machine. And for our case here, we choose to design an axial fan. So we hit OK. We know we want to build an axial impeller. And then we go through step by step through the design steps. And one thing is we have to decide, do we have a shrouded or unshrouded impeller? So in this case, it would be an unshrouded one. And I have to define the tip clearance, so the little gap between the blade tip and the casing. And I put it here to 1 millimeter. And then we have to choose the type of impeller. And we have two types here, so-called standard impeller and one thing for automotive cooling, which are specially thin and thin impellers. So the next we have to choose about airfoil and mean line design. So especially for these axial fans, the airfoil design is recommended. And then other options are here, which we do not apply today, would be multi-stage, control rotating, or even we can work with alternating speeds. So this is very specific stuff, let's say, for the aerospace industry. So this was the first step in the main dimension windows. Now, I talked before about the intelligence of CFturbo, and this is here behind the empirical functions. And for example, when you see here to define, let's say, how big your fan would be, you could choose these functions, which you see here on the left side, and the functions also graphical. And you see that CFturbo is not a black box. You really can control what you do all the time, and even these functions can be, what you have here, these functions can be adopted by yourself if you know it better, right? So, and so these are the input values. You have also to make an estimation of the aerodynamic and volumetric efficiency to make the right sizing of the fans, and then we get some numbers for the main dimensions. And let me think here. I want to check this. Calculate. Okay, anyway, so we use this number, basically what we have here. 165 and 330. So we can also adjust any of the numbers what we have in our model. And on the right side, we have a lot of graphical information, Cordier diagram, or also the main physical values here on this point of the design. Next design step would be the meridional view, and we can make this also here we can adjust the axial length of the fan. Now let me think. And we add a, let me think, I have to go back here for the main dimensions to check the setup. Yeah. Oh, here, this was the error. I have to go to standard. Yeah, I just choose the wrong option before. Yeah, go to our options, say calculate, and adapt here our numbers. And 300. So going back to the meridional shape, so we given a certain length, and again I could do this also manually. Add the hub and shroud. Can choose a certain solid design for the hub itself, and then I can come to the blade design. And here we, in this window, we define the number of blades which can be adjusted, and the number of spans. Spans we can see here. So it could be between at least 2 spans to 15 spans. I think here we recommend 10 at least. And we choose our design method for the radial equilibrium, and we usually say that we bring more work to the outer part in this case, and make a profile selection as the next stop. You can choose your different profiles, but we could also use our own point-based profiles. So this is okay. And we have a first design of our twisted blade. And in the final design step for the impeller, we could make a sweeping in axial directions. The sweeping of the blade is usually done for acoustic reasons, to minimize noise. And that's why, so there is a certain, let's say, drawback maybe in efficiency, but not much. And you have the chance here to adjust these sweeping models. And in this point, we already can see our 3D fan with 7 blades here, what we choose before, and 10 spans. So the second design step would be we add a stator, a vane stator, yeah, with blades, and we give them a certain extension. In this case here, so 90 millimeters would be enough axial extension. So this is pretty easy. Again, the same design step, meridional contour design. Yeah, we have the position of the leading and the trailing edge. This can be adjusted manually or graphically. So here we say, okay, Z constant. So we add these. We add again a hub solid and the shroud solid. And in the stator now, we calculate our blade angles. Same steps, number of blades. So this, we should be careful here because it's a matter that we should avoid pressure fluctuations. And in this case, so this is here supported in this window, that we can choose a higher number of blades. For example, number of spans, let's say 3 would be enough, I would say, because we choose a simpler blade shape. And we can choose different blade shapes from freeform, overruled surfaces, radial elements, freeform 2D or straight blades, and here we choose the freeform 2D blades. So we have a certain chance of changing the curvature. So on the other hand, in this window, we have to build in a certain thickness, and I suggest we make here a little profiling, make it thicker on the inlet and smaller on the trailing edge side before we can go to the next step. Again, we see here typical values, blade angles, meridian section. Next step would be the mean line design. So this is the curvature from the leading to the trailing edge. So everything is designed so far in the model, and then we can see this here. Here we have an inlet angle of about 50, outlet is 90 degrees. But if you want to say, okay, this might be not enough because we have some slip, so we should go back to the blade properties, change this blade angle to, let's say, 100 degrees. And we immediately see here in the mean line design our stronger curvature here in the for the blades. On the left side in the big window, this is a so-called MT diagram. This is the meridional contour coordinate over the tangential coordinate, and which gives us the possibility to see the true blade angles. And yeah, on the right side you see here blade passage area, or for example the static pressure rise in the stator, and we could do show many more of these details. Okay, next step would be then the blade thickness for the stator blades, and we can use this here. For example, we could use this by a linear interpolation, or we could also make freeform blades. So this is really a large variety, and when we have freeforms, again, we could have the possibility also to read in our profiles from a profile manager. So next step would be the rounding of the leading and the trailing edges, and this could be done in different possibilities, right, over simple elliptic or Bezier shapes. Here for the leading edge, we keep this elliptic, and the trailing edge, let's do this here on the Bezier, slim Bezier profile, and say okay. And with this, so we have a full axial stage of a fan. And now we add just some components on the inlet, on the outlet side, to prepare the computational model. So the one thing is we add an unvaned stator behind the vaned stator, given a certain length, certain extension, for example 300 millimeters roughly, and we say on the outlet we bring it down to 0. I want to build here a nice diffuser which decelerates the flow. What we do here is we split this curve twice to build a certain nice shaped diffuser. Sometimes it's also motor integrated or so, and we can change these curves. What we see here is the cross-section area. You see how the area is growing, which is good for the static pressure gain. And one more step. So we see this component right here, and finally we just add a piece of pipe which is for numerical reasons, let's say 1000 millimeter, that we don't have an influence from the components, from the boundary conditions to the components itself. So what we have on the outlet side, we also put in a nozzle on the inlet side to have a appropriate inflow conditions to our impeller, and this would be done here. We add a stator, given them a certain extension, right, and define the inlet from 0, and we make this a bit nozzle type, a bit larger, and finish it. And again, we modify our shape. We add here an inlet curve just to make a little recess, and we make a Bezier out of this. And on the other side, we built in a hub nose. We could also do this with a Bezier curve, defining the angle, the transitional angle. So, and this is basically our model which is ready for simulation and export. And what we do to check the geometry, for example, what we could do is a so-called model finishing of the bladed components. And I show this here for the impeller. Then what is done here? It's really he builds a solid. It's not only surface. He builds a solid model, and the same we will do here for the vane stator. And this is when this works. So then we will have no export issues. So we check these models. So and then we see our 3D model here on the screen. So, and two things which are pretty helpful. So we can, first of all, we could change colors and also change transparency, for example, from certain components. And the other thing is we can also rename components, which is helpful later when we use this in Ansys, because all the names and all the structure of the model will be used in Ansys, and we have this named selection option, which is really helpful for parametric modeling. So I use here these typical names. So this is a diffuser and an outlet extension. So this is what we have now ready for export. Yeah, when you see here, you see all the export formats which CFturbo is capable. So, and how we go in, or how we work then in Ansys Workbench. So this is then Sasha's part, and I would transfer, or I would ask Metin, please, that you make Sasha as the presenter now. From my part, I'm finished. Thank you very much.
All right, thank you very much, Ralph. So welcome everybody to today's session. In this session, I will be demonstrating the integration of CFturbo into Ansys CFD workflows by making use of the CFturbo Workbench extension. As Ralph already mentioned, the CFturbo Workbench extension enables the integration of CFturbo into Ansys workflows. It allows bidirectional parameter updates between CFturbo and Ansys Workbench. And a big benefit is that we automatically create named selections of characteristic turbomachinery patches for space claim exports. And therefore, it improves your data processing in Ansys meshing, CFX pre, and CFD post. And overall, you decrease the time you spend on the pre and post processing, and you fortify the robustness of your workflows. And of course, it enables you to perform automatic turbomachinery optimization using either standard tools like the Ansys Design Explorer or even external software like Dynardo's OptiSlang. Okay, during the installation of CFturbo, the user has the option to automatically install the CFturbo Workbench extension for all users of the workstation. After the installation itself, a new CFturbo entry will be created inside of the toolbox of Ansys Workbench. And we just start with an empty Workbench project, and we create a new CFturbo system by performing a drag and drop operation into the project schematic. We double-click the Setup cell to open CFturbo from inside Ansys Workbench. And once CFturbo has been loaded, we have the option to either create a new design or load an existing project. So for this session, we are going to use the turbomachinery design that Ralph created in the previous session. And by default, CFturbo displays the Meridian view of your turbomachinery components, and our current design consists of an inlet pipe, an axial impeller, a vane stator with an adjacent diffuser, and an artificial outlet extension. As Ralph already mentioned, it's in order to move our boundary conditions a little bit away from our design. In CFturbo, you can also display and animate a three-dimensional representation of your project design state. And on the left-hand side, you have access to all the components in the model tree, and you can configure their display settings individually. CFturbo also offers to export your visible model data to a 3D PDF document, allowing you to distribute and archive your 3D model easily. All of our turbomachinery components are fully defined by geometry parameters. So in the next step, we are going to configure our parameters and transfer them into the parameter set inside of Ansys Workbench. So I'm just going to open the Ansys Workbench menu. And as you can see, the available parameters of the project are displayed in a tree structure according to their components and the design steps. And each parameter can be activated or deactivated individually. So for today's example, let me just quickly collapse the tree view. For today's example, I want to activate, for example, the plate tip clearance of our axial impeller. Maybe I want also to activate the parameters for the impeller main dimensions, as well as the number of plates, which can be found in the plate properties module. And I could also activate parameters for our vanes stator. And in this case, I could choose also the number of plates, but for example, also the plate angle at the trailing edge. In the next step, we are going to configure our exports for our turbomachinery components. Therefore, I'm going to switch to the Export Actions tab. And for Ansys Workbench, CFturbo currently offers two export interfaces. The first one is the Space Climb export interface, which relies on a workflow using the Ansys meshing tool. The second one is the TurboGrid export interface. So in this session, we are going to export our impeller using the TurboGrid export interface. And we are also going to export our vane stator component to a TurboGrid system. And I'm just going to click that. And for the rest of our components, I'm going to use the SpaceCam export interface. So this would be the pipe in component, the diffuser, and the outlet extension. And on the left-hand side, you see a summary of the export actions we have currently defined. Okay, after we have successfully set up our export configuration, we will continue our workflow inside of Ansys Workbench. So we close all of our windows, we exit CFturbo, and we confirm the save dialog. And we are back at our project schematic inside of Ansys Workbench. As you can see, additional cells have been added to the CFturbo system. In detail, we have cells that contain the TurboGrid exports, and we have cells that contain the SpaceCam exports. Since we have activated parameters inside of CFturbo, a parameter set has been added to the project schematic. Inside the parameter set, you will find the parameters that you have activated in CFturbo. You can also change the parameter units to a format which you feel more comfortable with. And as Ralph already mentioned, CFturbo allows bidirectional parameter updates, which means that parameter changes inside of CFturbo are reflected inside the parameter set of Ansys Workbench. and also any modification to the parameters inside the parameter set are directly applied to your CFturbo design. So in the next step, we are going to link our exports of our Turbomachinery design to the corresponding systems inside of Ansys Workbench. This can be done by selecting the export cell, performing a right click, and choosing transfer data to new. And we are going to link TurboGrid exports to TurboGrid systems. And we are going to link SpaceClaim exports to Ansys meshing systems. All components are going to be meshed individually. And after we have set up this workflow, we are going to merge all the outputs from the meshing systems to an empty CFX system. Okay, so for now, no exports or computational mesh have been created. So in the next step, I would need to update my CFturbo system in order to create my export data. And since, for time reasons, since the export as well as the meshing process of my components is time consuming and we don't have that much time on the hand today, I'm going to switch to an already prepared Workbench project using the same geometry. As you can see, exports already have been created. I already have meshed the geometry. And let's take a closer look at the setup in CFX by opening CFX. And as I mentioned, named selections are created automatically for your Turbomachinery components. And you can use them inside of Ansys Meshing, CFX as well as CFD Post to apply your settings in a comfortable and more robust way. And so, for example, in CFX I have used them to set up my fluid domains. So normally you would need to deal with these artificial IDs if you haven't set up named selections manually. Like I said, CFturbo creates them automatically and you have access to them in this way. And you can also use the named selections for to apply your boundary conditions. So these examples are maybe a little bit trivial. So like I said, normally you would have to deal with these artificial IDs, but since our name selections are created automatically, you can just select them from this list. Okay. Yeah, in this, as you can see in the model, I have modeled all components as a 360-degree model, except of the plate passages, which have been modeled inside of TurboGrid. And of course, inside of CFX you have the option to quickly modify your setup and make a 360-degree model from your plate passages. So this can be done really easily by choosing the transform mesh option. We want to choose the option full circle for rotation. And of course, we want to have multiple copies. So in this case, I think the actual impeller was consisting of 7 plates. So we need 6 additional copies. And we can apply this change. And of course, we could perform the same operation for our vane stator. Also a full circle, but I think we need to have 8 additional copies since our vane stator was modeled with 9 plates. All right, and now you would just need to perform some small changes to your setup in order to apply for the changes we already have made. I won't do this now, so I'm going to switch to the results we have achieved with this design. So let me quickly open CFD post. And as you can see, I have already plotted the pressure distribution on the surfaces of our turbomachinery design. You can, maybe if we add streamlines, you can make it a little bit more clear. And yeah, if we take a look at expressions I have previously defined inside of CFX-Pre. So if we take a closer look at the hydraulic efficiency, at the aerodynamic efficiency of the impeller, you can see we achieve efficiency of around 90%. If we take a closer look at the efficiency of the complete stage, we still achieve efficiency of 80%. But of course, we need to meet our specified operation point. So if we take a closer look at the total pressure difference of the stage, you can see we only achieve roughly 450 Pascal instead of the 500 Pascal we put in as an operation point condition at the beginning. So we are short of 50 Pascal. So this is the first. So this is the first design iteration, and the design is a pretty good start, but we may need more iterations to meet our operation point or to increase our efficiency. And in this case, we would need to specify new geometry iterations by making adjustments to our parameters. So this can be done by going back into the project schematic, and I will show you how to easily create new design variations of your turbo machine. Okay, therefore I'm going to open the parameter set again. Inside the table on the left-hand side, you can see the parameter values of your current design. On the right-hand side, you can see the parameter values. Let me quickly move this a little bit to the side. So on the right-hand side, you can see the parameter values of all your designs, as well as the corresponding values of your output parameters. So in this case, you can see, as I said, we achieved an overall efficiency of 80%, but we were short of our total pressure difference. We only achieved roughly 450 Pascal. So what I have done is I have created a new design by just entering new values for my geometry parameters in the empty row below. And in this case, I have increased the number of plates for my impeller from 7 to 9. And I also needed to increase the number of plates for my stator to avoid that the number of plates are equal, which would be bad for noise reasons and would would induce pressure fluctuations. Therefore, I have increased it to 11. And then I just updated this design point. And if we take a closer look at our output parameters, you can see we lost one point in efficiency. So instead of 80%, we have an overall aerodynamic efficiency of 79%. But we achieved our operation point, which was 500 Pascal. So we have 505. And yeah, so we don't need to take a closer look at the pressure difference over the impeller, but we can see the values haven't changed by much. So we still have the same efficiency for our impeller. So this would be one option to perform some sort of manual optimization by just entering new parameter values by hand. And at last, I want to show you how you could perform an automatic optimization. So, for example, Ansys offers the design exploration suite, and we could choose, for example, a response surface optimization and just perform a drag and drop to the parameter set. And then you would need to define your conditions for your design of experiments. You would create a response surface, and you could run an optimization on this meta model that is going to be created. But this is some sort of more advanced topic, and I think we don't have much time today to dive deeper into this. So I think, yeah, we are open to questions, and yeah, thank you so far for taking part into this session.
Yeah.
Thank you, Sasha.
Yeah, thank you, Sasha. That was great. Nice way to show Workbench and CFturbo and how they connect with each other, which seems to be seamless. And I'll ask the first question. What we are looking at here is what do you think? How many engineering hours did you spend to do what you showed us here?
So normally, of course, tasks take different times. So, for example, Ralph showed you how to design your turbomachinery components, I think in roughly 15 minutes. Yep. So let's take this as a basis. So 15 minutes for your turbomachinery design or your initial design. And the whole setup until I start the simulation, for me, it normally takes something between 45 and 60 minutes, depending on how time-consuming the meshing process is. Mm-hmm. So overall, I would say after 60 to 80 minutes, I'm able to create a turbomachinery design from scratch and start the simulation. And then after I start the simulation, it's just the computing power that defines the duration of your whole process.
Okay, yeah. I mean, that's a huge time savings, which is the way to justify the use of CFturbo and Ansys tools in engineering design. That's an easy way to bring to managers' attention that these tools really help accelerate product design, in this case, the impeller design here. So thank you, Sasha. That was great. So I'm going to open it up for further questions from the attendees. Please, you can type your questions in the questions box, or I'm going to unmute everyone. Feel free to ask a question. Do we have any questions from the audience? Okay, we have one question: how the fluid domain is created?
So, well, I can answer that. So we can go back to CFturbo. The fluid domain is created inside of CFturbo. And what we are going to export from CFturbo is the fluid domain itself. And I can quickly show it to you. So I'm going to switch to the 3D model. And instead of recent state, I'm going to select fluid domain solids. And maybe I need to run the model finishing. So I need to activate the solid trimming because the solid trimming wasn't activated because we don't need it for TurboGrid exports, but that's no problem. It just takes a couple of seconds. All right, so yeah, that's a little bit, yeah, how do I say it? This is the fluid domain that is going to be meshed, except of course for the plate passages, because we use TurboGrid, and TurboGrid does not operate with fluid domains, it's more some sort of curve-based format. But of course, I could activate clipping, and maybe we would see how it looks inside. Yeah, so these are the fluid domains. So what's currently you see would be the volume where the fluid is transported through, and these are exported as in the step file format. We apply some script logic to modify the step files or to convert them into space-claim file documents and apply the named selections. And then the input into the Ansys meshing system is a space-claim file format.
Okay. Great, perfect, thanks. And the next question, can CFturbo work with Ansys Fluent?
So on a theoretical way, yes, but we use for our turbomachinery simulations, we use CFX mostly. We have talked to customers, and from as far as I know, I'm not sure about the limitations, but it's possible in a theoretical way. So
Sasha,
yeah.
Can I add? Yeah, it's not only theoretical. It is possible. We have clients which working with Fluent, yeah, from the automotive industry especially. I know customers which building automotive coolant pumps, for example, and they use Fluent. So that means the answer is a clear yes. In the end, I think a user has some preferences. So what we learned is that CFX is a bit more robust when it comes to compressible flow, especially, right? But to answer the question, yes, CFturbo works with Fluent, because then in the end it's only, I think, in Ansys Workbench what solver you choose, and that's it, right? Is it correct?
Yeah. So the main benefit is that we export fluid domains with named selections, and I think the way we connect the systems inside of Ansys Workbench. So let me quickly exit this. Sorry. So the way we connect these systems, if there's an CFX system or a Fluent system at the end, it does not matter by much, because what outputs comes from the CFturbo system is already a fluid domain with some sort of intelligence in form of the named selections for our characteristic phases like hub, shroud, plate side, leading edge, trailing edge, inflow, outflow. So yeah, I think it does not make any difference.
Okay, all right, thanks. Next question, CFturbo, can it provide any performance data before we run CFX or Fluent?
Yeah, I take this. The thing is, we have a certain empirical performance map estimation in it. But we would really say, if we want to make design decisions, and that's why we clearly follow the strategy that we should make 3D CFD, and we should automate, and we should make it quicker and quicker. And I think because you make design changes based on empirical models, and this is really not. It's a bit away from the truth, and that's why. So the answer is yes, it's possible, but we recommend to do CFD.
Right.
Right.
Okay. Thanks. How does CFturbo handle small features in geometry?
This depends. Small features is from CFturbo not a problem in the sense. So it's in a way it's a CAD system. The question is, what type of features are needed? So we have limitations in let's say in building some features, right? But the question is, small is not an issue. The question is really what should be built. But when we talk about a small tip clearance, this is not a problem at all, right? And depends a bit. The question should be, or the person who asked should elaborate a bit more what type of small structures he means.
Okay. Yeah, if you can please type it in the questions box, the person who asked the question about handling small features, that would be great. I'll jump over to the next question. And sorry, these questions are coming at random, but I think this is related to the previous question. CFturbo does not have any empirical relation for very initial stages of design. Is that correct?
What we have empirical correlations to make our designs. So all our designs are based on empirical correlations.
Okay.
So and so that means, or as I demonstrated in my presentation, so we have empirical data to create geometries, right? The sizing and the blading and all this thing. What we don't recommend is loss model based performance map estimation. Also, this is maybe this. I don't know what the question means, but I think so. Empirical data, yes, for creating the geometry. However, for making performance data or getting performance data, we should run 3D CFD.
Yep, and that's why the parametric relationship comes in very handy, so that we can do that design space. Okay, great, thanks. Next question, can you do heat transfer with your modeling CFX? And that I can answer. The answer is yes. We can do a conjugate heat transfer simulation in CFX. And we need to add the solids, of course, in this case. Is there something else you would like to add, Sasha?
Yeah.
Or
yeah, I would add. We can do solids. We can add solids to a certain extent on our side, especially from the impeller and stator side. So what we don't have yet is solids for the casing. You know, for imagine a volute casing, so we don't have the solids over there. So this must be added then in Ansys at the moment, but we work on this so that a user can one day also have full solids. That's clear.
Yep. All right, thanks. Next question. For a lone sprinkle design, can the pump design be imported back and forth between a CAD system as well and then moved to Ansys?
Yes. So the thing is, the way is today the following. So we import a, let's say, a CAD file, a step or parasolid file, for example, to CFturbo, or also it could be also SDL data, so we can read it in. And then we rebuild the model. So this is a bit manual work, but we can rebuild it, right? And then bring these rebuilded model to Ansys as we have seen it here today. It's a possibility, and we are in a process in make this more and more, let's say, user-friendly and comfortable. But in general, it's already possible, yes.
Okay, thank you. Next question, will you recommend, this is probably for Ralph, will you recommend a Turbomachinery design handbook as a reference?
The Turbomachinery handbook?
Design handbook.
Oh, I'm not familiar with this, I must admit. So maybe this answers the question. The thing is, so our data, what we use is from, let's say, from different well-known professors, right? In the pump side, for example, it's Gülich or Stepanov or Lobanov, right? Compressor side is Professor Casey or Lüdke, Kamsky, and so we are using all these, let's say, well-known data from which are around, but also some research papers. And so the Turbomachinery design handbook. So I would be interested to see this. Yeah.
Okay, or just buy CFturbo from us, then that will be okay. Thanks. All right. How is meshing affected by small features in geometry? That I'll take that if you like. Or Sasha, would you like to respond?
No, I'm waiting for your answer, and then
Okay.
I'll feel free to
So,
comment.
yeah, I mean, what we do is, in general, when we do these type of projects, we make sure that we have a what we call quote unquote mesh independent study. So that mesh independent study means that the grid that we build into the CFD models, after we refine it, the results do not change anymore. That's what we call a mesh independent study. So now, if you have very small features, very tiny features, again, we can take that into account. The only challenge is in the vicinity of those small features, we are going to put a lot of cells, a lot of elements in the grid. So it's going to increase, of course, the computation time, but that's not a problem these days. We have access to cloud computing or other fast computers. So depending on what you would like to get out of the study, the answer is yes, we can take into account a lot of small features and really come up with a simulation that will look into the flow field around those small features. Is there anything you would like to add, Sasha?
No, that's all. I think that was a very good explanation. So I have to admit there are no problems with small features. It all depends on the meshing tool. So small features with TurboGrid are not a problem, and small features inside of Ansys meshing just depends mainly on your mesh settings and how far you are willing to refine or how far you need to refine in order to achieve a mesh independent result.
Okay. And last question. Thanks. So can CFturbo models merge with additional CAD to build an assembly level model?
The thing is it the same what I said before. So we cannot merge it in CFturbo. So the thing is, if these existing CAD is let's say Turbomachinery components we can build in CFturbo, then we could rebuild the whole thing. But I assume the question goes in the direction if someone has, let's say, an existing casing, for example, right? And he want to merge this casing with the CFturbo file. So then this has to be done in Ansys Workbench then, right? Not in CFturbo. These merger then.
Well, I would like to add, it's possible in a way when you just want to add adjacent components. For example, you have some sort of inflow geometry to your pump or to your fan, which is fixed because these are neighboring components. So in this case, it would be possible to integrate them into the workflow, just for example by creating a geometry system, loading in your or importing your geometry and then meshing it and transferring it to CFX. What's not possible is to some sort of create CAD workflows inside of CFturbo when you start to trim away and to unify or to split with geometries of CFturbo. That's not possible. But for simple adding them to neighboring components, that's no problem.
Okay, great. Okay, well, thanks everyone. We did go over time, but thanks for your patience and thanks to our speakers, Chelsea, Ralph, and Sasha. That was a great presentation. And for those of you who may be interested in further in the software, if you'd like to see a demo, if you'd like training, consulting, please contact us. These are our numbers. And of course, if you are interested in CFturbo software and Ansys, please contact us. So we started out this really exciting relationship with CFturbo and we do have a good marketplace here, and so we would like to we will plan on doing further webinars, and so yeah, please keep in touch and please contact us if you'd like to, if you have any further questions that have not been answered here. So thank you for your time. Have a great rest of your day, and if we don't talk to you, have a great holiday season in the rest of December. Thank you.
Thank you, Martin.
All right.
Thank you. Have a good day. Bye.
Thank you very much.
All right. Thanks.
Goodbye.
All right. Bye-bye.